Welcome back to the deep dive. Today, we're getting into something highly specific. We're looking at a single piece of hardware, the NTI E-ACLM-3P480 three-phase AC power monitor.
Right.
And our mission really is to unpack not just what it does, but why this level of detail about power is so critical for, data centers, hospitals,
Well,
all the big stuff.
it's like finding the pulse of the building's power grid.
Exactly.
And that name, three-phase, is the key. For anyone listening, this isn't the outlet in your wall. This is the heavy-duty, stable power that runs entire commercial buildings.
The big leagues.
The big leagues. And this device, it's basically an auditor for that system's electrical health.
Okay, so the specs say this thing tracks seven different electrical metrics. That sounds like, well, a lot to keep an eye on, especially if something's going wrong.
It does, yeah. We're talking true RMS voltage, RMS current, frequency, active power, reactive power, phase angle, and power factor. It's the full panel.
The whole diagnostic.
But here's the really interesting part, the key detail from the source material. Yeah. While it shows you all 7 of those for diagnostics, it only uses 4 for data logging and for triggering alerts.
Wait, only 4? Which 4?
Just the core ones. RMS voltage, RMS current, active power, and reactive power. It tells you the design is all about operational stability, not just academic readings.
I see. So it filters out the noise.
It logs only what signals immediate risk or a load balance problem. And it does that for each phase, individually.
That makes so much more sense. It's built for action, not just analysis. So we know what it measures, but how do you actually install something like this? The input capacity is, what, up to 552 VAC?
Yeah.
We're definitely not just plugging this in.
Oh, absolutely not. That voltage means you're tying into serious commercial power, and it's designed for one single or 3-phase circuit. It can't, for example, monitor a bunch of separate independent circuits.
It needs a unified system.
Exactly.
Yeah.
And that brings up the most critical point.
Safety.
First, you need what are called current transformers, or CTs. Think of them as sensors. They let the monitor safely measure huge currents without being wired directly into, a lethal amount of voltage.
And those are sold separately, I saw.
They are. And second, and this is the big one, the voltage inputs connect directly to the live line. So this has to be installed by a qualified electrician.
Right.
And the main electrical service for the building must be shut down first. No question.
That sounds complex and involves some risky downtime. But you see these in data centers, telecom substations, even medical equipment. The payoff must be worth it.
In those places.
Yeah.
100%. You're basically buying operational resilience. And the strange thing is, once it's installed, it's incredibly simple.
How so?
It's described as plug and play. It's a pure hardware design.
Yeah.
No software, no drivers to update. That's perfect for environments where you need absolute stability over fancy features.
And the reach is pretty impressive, too. It uses standard network cable up to 300 feet, but you can get an extender to push that out to 1.2 miles.
Yeah, think about that. You could be monitoring a remote power substation or a generator across a huge factory floor from a central office.
Right, without a complicated IT setup.
It's all about providing that continuity, that constant stream of data across a distributed system.
So ultimately, this device just strips away any ambiguity about what your power is doing. It's not just on or off. It's a real-time health report.
Precisely. And that leads to a final thought for you to take away. Given that this hardware is explicitly designed to show 7 metrics but only log 4, how often do you think that tiny difference, the choice of what data to ignore, is the very thing that prevents a catastrophic power failure in a hospital or a data center?